Let's start in section 1.1, which is on Introduction to Systems of Equations. So first up, what is a linear equation? Well, the common quality that linear equations have is that all of the variables have an exponent of 1, and each term has at most one it has at most one variables. Uh, let's see. I've got several examples here. This first bit, this is what you probably think of when you think of a linear equation. People instantly think y equals mx plus b. And that's the slope-intercept form. And that's useful. That's really useful if you're graphing. If you're graphing a line, the slope-intercept form. Because the m, of course, is the slope and b is the y-intercept. Now this next one is called the general form. Actually, the rest of these are all general form. General form, when you're just looking at a line in the plane, general form is nicer because you can represent any line you want to with it. You might say I can do that with the slope-intercept form, but there's one type of line you can't do with the slope-intercept form. You can't do a vertical line. So anyway, general form is what we're going to mainly use in this class. Just for a few non-examples, let's see, these are not linear equations down here. This one, because there's an exponent of 2, so it's immediately not a linear equation. This is not a linear equation either because it's got x and y multiplied together. So we wouldn't call this linear. And same thing down here. Problem with this one is we've got this 1 over x, which is like x to the negative 1 power. So that's not a linear equation. So the general form for a linear equation, just in general, is this, where you've got a1x1 plus a2x2 and so on. The b is called the constant term, the x's are the variables, and the a's are the coefficients. All right, so one of the first things I want to do here is talk about linear equations and how they relate to points in the various spaces. Three-dimensional space, two-dimensional space, which is the plane, but we'll start with one-dimensional space, which is just the real number line. If I draw the real number line here, we can think of that as a one-dimensional space that you could move back and forth on. So if you have just a single equation, let's say we have the equation 2x plus 1 equals 6. Well, if we solve this, we get 2x equals 5, so x is 2.5. So if this is 0, then 2.5 is somewhere over here. And that's our solution. Now you might say, this looks like intro algebra. Well, the point I want to make with this is what we've got is we're looking in a one-dimensional space, and a single equation designates a single point here. And that single equation gives us enough stuff to cut the line in half. Because this is here, and there's this half on this side and this half on this side. And also, it takes one equation to designate a point. Same thing here. 3x minus 5 equals 1. We could solve that. Get 3x equals 6, x equals 2. And the thing I want to point out here is this is what we think of as the problem, and this is the solution. But they're really both linear equations. It's just that x equals 2 is sort of solved out into a nice format for us. All right, let's go up to 2 dimensions. 2D space is the xy plane. And an equation in the xy plane designates a line. And that line cuts the plane in half. If we were to draw this out, and here's some line, that line, we've got the half of the plane above and half of the plane below. But if we wanted to designate a point in the plane, what we'd have to do is specify 2 different lines that intersect in one point. So this system over here, this is a system of 2 equations, and I want to solve it because these 2 equations, either they're parallel lines or well, either the lines have the same slope or they intersect somewhere. And if they intersect, that's the solution. So let's solve it. You've probably learned different ways to do this. My cat has been here in my lap the whole time. You probably learned how to do this with substitution and elimination. And elimination is what we're going to use in this class because we're going to learn a generalization of it that's really efficient. And anyway, let's do this with elimination. Now, the first thing I notice on this is I've got a 4 and a negative 1 here for these. So I'm going to multiply this bottom. I'm going to multiply this by 4. And so my top equation stays the same. My bottom equation becomes 4x minus 4y equals 32. And I can add these up. Now when I add them, I get 7x equals 35. So x is 5. And y, I could plug back into either one of these things to come up with y. That second one is going to be the easier one. So if I take that and I plug it into 5 minus y equals 8, then y is going to be negative 3. So this is my solution. And notice again, my solution is also just a pair of linear equations. Of course, these are nicer than these up here because we've eliminated some stuff so that one of them is x equals something and one of them is y equals something. Makes it really easy to go over and find them. Let's graph that just for fun. If I come over here to Desmos and graph it, let's see, it looks like I already had it there, but I'm going to put it in again anyway. I'll just put in 3x plus 4y equals 3, and then x minus y equals 8. And graphs the two things, and sure enough, 5, negative 3 is where they cross. All right, let's look at three-dimensional space. Now, in 3D space, or R3, an equation designates a plane. And like before, a plane cuts space in half. And so if you have two non-parallel planes, then those planes are going to intersect in a line. And it takes 3 equations to designate a point. And I want to look at that by looking at this plane graphing tool. This is on my website, but let's see. So red, green, blue. Red is the x-axis. Green is the y-axis, and blue is the z-axis. So let's look at a plane here. I'm just going to put these coefficients in. Let's say we have the plane x plus y plus z equals 0. That's this plane here. Now let's put one in that we... Okay, that's the plane z equals 0. If I change this to z equals 1, it looks like this. Might make more sense to put the z-axis going up. There we go. And if I start putting things on here, like let's say I put a point 1 here, that's going to tilt it a little bit in one direction. If I put a 0.5 here, it's going to tilt it a bit in that direction. But this is a single plane. If I put another plane here, these two planes intersect in a line. You can kind of see that line. We can see it really good right there. But if we wanted to have a single point designated, we'd have to put a third plane in there. And sure enough, 3 planes, they intersect in a single point. But like before, notice it. 2 non-parallel planes designate a line, and it takes 3 equations to designate a point in 3-dimensional space. So we're going to come back to that a little later when we're looking at solutions of systems, because thinking of equations in terms of the lines or planes that they represent, that's going to be a useful thing to visualize later. So we'll stop this video here and we'll pick up in the next one.